Welcome to 5.1. We will start a new chapter. This time it is vector fields. What is a vector field? A vector field is like a slope field that we learned in calculus, but or calculus 1, but it's a where direction actually matters. So if we drew the slope field of y dx equals x plus y, then we'd have something like that, or like that, like that, like that, that. That's where all the slopes 1, and then this is where all the slope is 2, and then this is where all the slope is 3, right? And we'll have something like that. But slope doesn't exist in 3D. It doesn't. So instead, what we do is we use vector fields. Right? So if we go, if in this picture we were to go to the left, are we supposed to go left up? No, we're supposed to go down. So slope is a little bit misleading in this case because if we go down, like if the arrow was up like this, if we actually had a vector, then we'd know that, well, yeah, we're supposed to go up like this. Or the at least there's a force or something, the disturbance that is making us go up. But if it's going down like this, then we don't really know. We kind of have to rely on the our intuition to realize how the path is going. Because if we were going to the left, it doesn't mean that we're going up, or it doesn't mean that we're curling. It means that we're going down. It's a little bit strange. Vector field's gonna clear it all up. We use a vector field, usually for 3D, but also for 2D as well, in order to visualize things, easier. So what is the vector field, or what is these? I'm sorry, not the slope field, the vector field. Draw the vector field of f. So the vector field of f is f. Okay, I should have bolded f because it's supposed to have like a hat on top of it. So it is a vector field, not a scalar field or a slope field. So when y is equal to x, they're all the same. Or no, I'm sorry, I lied. So when y is equal to x, or no, when x is equal to 0 and y is equal to 0, there's nothing. When y is 1, or so yeah, so let's stay on the x-axis. So when y is, or the y-axis, I'm sorry, let's stay on the y-axis. When x is 0, y is 1. Then we have 1 comma 0, so it's like up like this. And then when y is 2, we have 2 comma 0, so it's like this. And 3 comma 0, so it's like this. So the slopes get bigger. And similarly, when it's negative, it gets smaller. What about negative x? So negative x means that um, now we're going down. Well, negative x means that we're going to the left every single time it's right. So at 0, that will just be this. And then if we continue going through the x-axis, it will grow bigger and bigger. And usually sometimes we can't really use size. So what we'd end up using instead is the not size but color. So color can be used to indicate vector field strength as well. What about 1 comma 1? At 1 comma 1, it's negative 1 comma 1. So it's something like this. At 2 comma 2 is negative 2 comma 2, so it's bigger, and it gets even bigger. And in fact, the pattern looks to be something like this. So what is this pattern? This pattern is, it's trying to flow up and it's trying to flow down, right? So you can actually computer simulate these some of these patterns to figure out how the behavior of um, something that a vector field imposes on will change over time. So in this case, it will be if you put a particle in here, if it doesn't get past, or yeah, if you send a particle with a fast enough speed, it will move down. But if you send a particle and it's not fast enough, then the forces will bring it up, and it will bring it up closer and closer to this axis right here. So similarly, it'll look like this, and then like this, right? And then like this. So that's how the slope field will look like. It will be quite it'll be quite annoying, honestly, to draw slope fields every time. So we're not going to draw a slope field most of the time. However, you need to recognize what these slope fields do. And these, I just exaggerated them, even though they're not supposed to be that big. So yeah, that's the behavior. The main point is to realize that the behavior, or that the arrows are moving closer and closer to the y-axis. That's the main point. So more vector fields. These are some vector fields in 3D. Obviously, it's a lot harder to draw in 3D. And this is illustrating some kind of swirly behavior. This vector field right here is just all going closer, yeah, closer and closer to the z-axis. And then this vector field right here is strange. I think it's a less version. It's less extreme version of this. I don't know though. It's strange. It's a strange vector field. We can't usually draw vector fields in 3D. However, we can somewhat draw this vector field right here. And usually when you draw vector fields, you see them in these box kind of containers. And how we're going to draw this? Well, if f of x, y, z in this case is x times j hat, that means f is equal to 0, x, 0. So at x equals 0, which is this entire plane right here, there are no vectors. No vectors in the vector field. At x equals 1, it's going 1 in the y direction. At x equals 1, it's going 1 in the y direction. That's a little bit strange. Alright, so I'm actually going to mark this as 0. I'm going to mark this as 0. This is x, this is y, and this is z. So at x equals 0, nothing happens. At x equals 1, which is right here, it's going 1 in the y direction. So x equals 1, x equals 1, x equals 1, x equals 1. At x equals 2, it's going 2 y direction. Similarly, at negative, it's going -1 in the y direction, -2 in the y direction. And it's basically that same thing stacked on top of each other again and again and again for the z-axis. I don't want to draw all of the arrows because it'll look very messy and you guys will probably be more confused. But it's that same plane stacked on top because the z doesn't do anything. It doesn't do anything to the z either. So it's just that xy plane really is the only place where it matters. So these are some examples of the vector fields in real life. Very useful for stuff like electricity, wind patterns, weather patterns, um, yeah, ocean currents, airflow past just to like minimize drag and stuff like that. Fluid motion, when fluid moves through a pipe, you can model its velocity. So that's those are some vector fields in real life that you will see. Now, the first definition of this chapter is the gradient field. What's a gradient field? A gradient field, well, what's a gradient, first of all? Gradient is this right here. When you have a function f of x, y, or f of x, y, z is equal to like 2x plus y, the gradient of f is the partial derivatives 2 and 1. Right? So that's the gradient of f. But what's a gradient field? A gradient field is a field f. So yeah, this is always a gradient field. This is a gradient field. But if we're not given that that's immediately a gradient, then we have to figure out whether or not it's a gradient field by itself or not. So f is a gradient field when or f is a gradient field when the x component is or yeah when the x component of f is the partial derivative of x of a potential function of a function. And then f sub y is also the partial derivative with respect to y of that same function. That is a gradient field. And the gradient field, yeah, is a gradient field, and the function that originates, it's called the primitive. So the primitive of f, the function that originates from f, is called a potential function. So field, the electric field, and the potential function associated with it is, you could say that, and it's not very accurate, but if you want to use a Calc 1 analogy, f, or the gradient of f is equal to f. So that's like the derivative of f is equal to capital F. So the integral of capital F is equal to f. Something like that. So that's the potential function. Integral of the field is equal to the potential function. But obviously that's not very accurate, and we're going to find another way to express that later on. So are these potential functions? First of all, how do we find potential functions? Um, so we realize that, well, potential functions probably going to be continuous. I'm gonna I want to make the assumption that all the potential functions that we're gonna work today, or we're gonna work for the rest of the course, is going to be continuous, or else it's gonna be very, very hard to do. So if it's continuous and its partial derivatives are continuous, so it's differentiable, if these are continuous as well, then we can realize that, well, f sub x y is equal to f sub y x. That's a Clairaut's theorem. That is a theorem that we have proved. Oh no, we haven't proved, but I've shown you, and that's what we use to exploit in many of the problems that we did for chapter 14. So what does this mean? This means that, well, if I put f of x and f sub y to m and n, which are common letters used in this case, then m sub y have to be equal to n sub x. That is the condition. The condition for a gradient field is the left function derivative of y, or derivative with respect to y of the left function has to equal with the derivative with respect to x of the right function of yeah, so n sub x, because f sub xy is f sub yx. So what does this mean? This means that, is this the gradient field for potential function? It is exactly not, because m sub x in this case is, or and I'm sorry, m sub y in this case is 1, and n sub x is totally 0. Is this a gradient function? M sub y is 2x, and n sub x is 2x. You betcha it is a gradient function. Is this a gradient function? M sub y is what? M sub y is x, but n sub x is negative y, not a gradient function. So the only gradient, sorry, not gradient function, gradient field, the only gradient field is this one. That's the only gradient field. These are not gradient fields. They cannot be turned into a potential function. They're not integrable, basically, in the Calc 1 sense. Um, so I don't know where that page is. Line integrals. Line integrals. All right. So let's find the gradient field for some of these functions, right? Let's find the gradient field. So g of xy is this. If g of xy is this, then what's the gradient field? The gradient field is the gradient of g, which is 6x squared negative 6y. Very simple. What's the gradient of h? The gradient of h is a little bit tougher because there's a bunch of variables and stuff, but it's 3 dimensions. You do the same thing. Y e to the y, comma, or no, not y e, not comma yet. Y e to y minus e to the x z squared, because this entire part is integrable, and this is the only constant with respect to x. And then for y, it's x times y e to the y plus e to the y product rule. And then for z, it's negative 2z e to the x minus sine z. Now finding this gradient function will be would be very annoying. And I'm gonna tell you how to find this soon with 3 variables. How do you find it? So it's a gradient field. So how do you test for to see if it's a gradient field or not? I'm gonna tell you how to do that. But uh, these are just very nasty numbers, and that's why it's dumb. All right, so let's find some gradient fields. It's a little bit more complicated. It's a little bit complicated to find a gradient field. Because worried about we're no longer just worried about constants when we integrate. We're also worried about things that we treat as constants. So what does that mean? That means that f sub x is x and f sub y is negative y. However, in our original function, we could have done f is equal to, um, let's say 1/2 x squared minus 1/2 y squared. And I think I literally just found the function for this. But yeah, we could say f is this, and f sub x is equal to x, right? If we integrate this, we get f is 1/2 x squared plus c, right? If we integrate it with respect to x, we'll get 1/2 x squared plus c. But look at its original function right here. 1/2 x squared minus 1/2 y squared. It doesn't include c, but when we integrate f sub x, or when we differentiate with respect to x, it doesn't include y, but when we differentiate it with respect to x, you still get x. So this c can't just be a constant with respect to x, or a constant, regular constant. It can also include y stuff in it, because everything that we have with y got canceled out when we did the derivative with respect to x. So I'm going to say that this is c of y. It's a function c. It's a constant function. It was what we call a constant function when we do our integral in calculus 1, but it's with respect to y because it can include y stuff in it as well. So how do we find that out? Well, now we do f with respect to y, right? So now we take this f right here. This is kind of the algorithm. So if we take this f right here, and we would differentiate with respect to y. So what's 1/2 x squared differentiated with respect to y? 0. And what's c of y with respect to y? It's c prime of y. So what are we getting? We're getting c prime of y is equal to negative y. So what's c of y? C of y now is negative 1/2 y squared plus c. And we've exhausted it because this is c of y only. It's not, there's no x stuff in it. It's negative 1/2 y squared plus c. So now we know that f is 1/2 x squared minus 1/2 y squared plus c. And that is the potential function for capital F of x, y. So in 3D, it's a little bit harder. In 3D, you have different combinations. You can have f sub xy is equal to f sub yx. You can have f sub xz is equal to f sub zx. You can have f sub yz is equal to f sub zy. So you can have these possible combinations right here. P sub z equals r sub x. So that's f sub zx and f sub xz. You can have q sub z, r sub y, and then you got p sub y, q sub x. So all 3 of these have to meet in order for it to be a vector field. Let's see if this is a vector field. Let's do this first condition. P sub z is equal to r sub x. So P sub z is what? P sub z is y, and then r sub x is what? R sub x is y. So yes, that meets. Now, what about q sub z is equal to r sub y? So q sub z is what? Q sub z is x, and r sub y is also x. So that means, what about p sub y is equal to q sub x? So p sub y is z, and q sub x is z. So that means, so this function is a vector field, or it's a gradient. It is a vector field. It's a gradient field. This is a gradient field. And that's gonna be it for today's lesson. I think, unless if I got anything else. Yeah, that's gonna be it for today's lesson. If you enjoy, hit the like button down below, subscribe, share to everyone who didn't get to do line integrals for their Calculus 3 course. I find that very unfortunate, but the show must go on, and I'm here to save those people. Um, I will see you guys next time, and yeah, next time for line integrals.